So let us continue with our discussion on wet compression vapor compression system with one more problem. So the problem is given by, in an ammonia vapor compression system, the pressure in the evaporator is given by 2.1 bar, and the ammonia at the evaporator entry, that is entry to the evaporator, is nothing but the 0.4 or X4 is given by 0.19 dry, and at the exit it is 0.86 dry, that is exit of the evaporator is nothing but our state 1 or entry into our compressor. So X1 it is given as 0.86. During compression, the work done per kg of refrigerant is 150 kilojoules. Here, instead of mass flow rate, the mass of refrigerant is being given. So when we are finding this work done and all, it will be in kilojoules rather than kilowatt. Calculate the COP and theoretical piston displacement of the compressor if the mass flow rate of the refrigerant is 4.5 kilograms per minute. So mass flow rate is also given but separately. So here the specialty regarding this question is that in comparison to the other questions where temperature was given, here it is given in terms of pressure. That is, only the evaporator pressure is given. No information regarding the temperature or the pressure of the condenser is given here. That is, this value of TC, PC, etc. are not known. We only know the pressure of the evaporator to be 2.1 bar. So we can write the data given as the temperature, rather the pressure of evaporator as 2.1 bar. Also the dryness fraction at evaporator entry rather at 0.4 or X4 as 0.19, and dryness fraction at evaporator, its evaporated exit rather, that is at the exit of the evaporator or the compressor entry as X1 is equal to 0.86. It is also given in the question. Also the work done per kg of refrigerant, W is equal to 150 kilojoules per kilogram. Also mass flow rate of the refrigerant, M dot as 4.5 kilograms per minute. We are not converting that into kilograms per second. Also here, since the question is slightly different, we don't know the conditions regarding this condenser, it is better to do this problem analytically. Also, since this is given in terms of a pressure, I think by using the refrigerant table for R717, or ammonia is the refrigerant given here, we can find that temperature corresponding to minus 18 degrees Celsius, the saturation pressure at that point is something more or less near this 2.1 bar. It is 2.09 rather. So we can take 2.1 bar as the pressure or saturation pressure. So the corresponding temperature of the evaporator can be taken as minus 18. That is, what we did is that we just searched the refrigerant table of ammonia. By trial and error, we found out that at temperature corresponding to minus 18 degrees Celsius, the saturation pressure of the refrigerant is nearly 2.1 bar. So we are taking the values at minus 18 degrees Celsius as the values corresponding to 2.1 bar, and we are taking the values of VG, HF, HFG, HG, SF, SFG, and SG. That is the evaporator conditions. Now, using the dryness fraction, we can actually find the enthalpies at state 1 and 4, that is H1 and H4, and also the specific volume of the refrigerant at compressor entry, since it is given to find out the piston displacement. So we have all the data needed here. So H1 is given by HF corresponding to 2 bar plus X1 into latent heat HFG at 2 bar. By taking from the values in the table, it will be something like 98.76 plus 0.86 into 1323.96, which gives H1 to be 1237.36 kilojoules per kilogram. Similarly, H4, we know the X4, or at evaporator entry, the dryness fraction was 0.9, so it gives 98.76 plus 0.9 into 1323.96, which gives the value of H4 as 350.31 kilojoules per kilogram. Similarly, H4 will be equal to H3, so we can get H3 to be something like 350.31 kilojoules per kilogram. Also, the specific volume of the refrigerant entering the compressor, that is entry to compressor, entry to the compressor, V1 is given by x1 into Vg, that is Reynolds fraction at state 1 into the volume of specific volume of vapor corresponding to 2 bar, which is actually given by 0.86 into 0.5750, which gives the value to be 0.4945. Here we are not using this plus Vf term, since the Vf will be very much smaller compared to Vg. So x1 into Vg is enough for calculating the value. This will approximately give the accurate result. And this is with reference to the properties of pure substance in thermodynamics. So we got the enthalpies at 1, 3 and 4 as 1, 2, 3, 7, 350, etc. Now we can find the refrigerating effect, which is nothing but H1 minus H4. So we know got the values of 1 and 4 enthalpies, which being 1, 2, 3, 7 and 350, we'll get our refrigerating effect as 887 kilojoules per kilogram. Since the work done is also given in kilojoules per kilogram, we can actually calculate the COP without knowing the work flow rate or mass flow rate. So for finding the COP is given by refrigerating effect by work done. Already the work done was specified to be something around 150 kilojoules per kg of refrigerant. So substituting the value 887 divided by 150, we'll get the COP of the system to be 5.91. Then for finding the piston displacement, we have two formulas rather, mass flow rate into specific volume at compressor entry divided by the efficiency of the compressor, or we can use our formula related to piston as LANK by 60, but here there is no information regarding the piston bore diameter or the speed at which it is working. So it is better for piston displacement to use the formula mass flow rate into specific volume at 1 divided by compressor efficiency. Since this is also not given, we'll assume this value to be equal to 1 or 100% efficient. So we can directly substitute the mass flow rate in terms of kilograms per minute, that is 4.5 kgs per minute, into V1 or specific volume of the refrigerant entering the compressor as 0.4945 meter cube per kg, which will give our piston displacement as 2.225 meter cube per minute. Thank you.